Hello there, my name is Vinay Kumar and I'm a PhD student in the EC department at the Indian Institute of Science, and this is my video on my research on probabilistic broadcast mechanism for ad hoc networks. Let me begin with the motivation for my research. Let's suppose you have a field in which there are some sensor nodes deployed. These could be temperature or humidity sensors, and they form a network. It's a noiseless communication links that I have indicated here. Let's suppose that there is a particular node distinguished as the source which has some information that it wants to broadcast. This could be like updating the sensing frequency of all the nodes in the network. An alternate application that you can have in mind is that of the Internet of Things, where the source wants to do over there programming of the IoT nodes. In both these scenarios, we are interested in to broadcast information in the network, but with the following constraints. The constraints on the nodes are that they are energy constrained, they have no knowledge of the network topology, and they have limited computational ability. In order to account for these constraints, any algorithm that we propose needs to be completely distributed and should run in finite time. In this work, I'll be mostly interested on more large and dense networks, and I'll assume no interference or packet loss. A naive algorithm for broadcasting is what is called as flooding. Let me explain flooding using this small graph of 4 nodes, where the yellow node is the source which has 2 packets that it has to transmit, packet 1 and 2 with information x and y. In the flooding mechanism, whenever a node receives a packet, it blindly transmits it to all its neighbors, and this it does to each of the packets it receives. Here there are 4 nodes and 2 packets, and hence there are 8 transmissions. Let us take a look at the simulation of this flooding mechanism on a large graph. The plot here plots the number of transmissions and it gets updated with time. Generally, on a graph of n nodes with k data packets, there are total number of transmissions is k times n. However, so here there are 101 nodes with 2 packets and hence 202 transmissions. Moreover, all the nodes in the network receive both the packets, and hence the fraction of receivers is 1. However, there are many unnecessary transmissions because a particular node might receive the same packet from multiple neighbors, and hence there are wasteful transmissions in the network. In order to overcome this, an alternative that has been proposed in the literature is what is called as probabilistic forward. Let's go back to our example of a small graph. Here again, you have 2 packets x with information x and y. In probabilistic forwarding, the source transmits each packet to all its neighbors, and every other node in the network tosses a coin with probability p and transmits it if it lands heads. It does not transmit it if it lands tails. And this is done independently to each of the packets by each of the nodes. Notice here that there are just 6 transmissions, and all the nodes in the network have received both the packets. Let's again see a simulation of this on a large graph. So in this, I have taken the forwarding probability p to be 0.8. The yellow nodes here are those that receive the packet and transmit it. Blue nodes are those that receive the packet but do not transmit it. And the red nodes are those that do not receive the packet at all. Notice here that the number of transmissions is 147. Again, if you have a graph on n nodes and you have k data packets with packets being forwarded with probability p, the expected total number of transmissions is at most k times n times p. Notice that if you have a non-trivial p, if the p is less than 1, this is certainly lesser than the number of transmissions that you had in flooding. The number of transmissions there was 202, here it is 147. However, this results in a new problem that a particular packet may not be received by some of the nodes. Even if one packet is not received, the information from the source is lost. And hence, if you account only for the nodes which received both the packets, the fraction of receivers is 0.693. Our aim in this work is to improve upon this fraction of receivers, while at the same time keeping the number of transmissions to a minimum. And we propose a new algorithm called as probabilistic forwarding with coding in order to do this. How does this work? Let's go back to the small example that we had. Again, you have 2 packets, packet x and y, and the probabilistic forwarding happens as before. However, the second packet, both of these nodes toss tails, and the node on top does not receive the packet. What the source does in such a situation is that it encodes a third packet with information x plus y and does the same probabilistic forwarding protocol. The source transmits to all its neighbors. Every other node in the network tosses a coin with probability p and transmits it further if it lands heads. Notice that because of the coding mechanism, any node in the network which receives at least 2 out of these 3 packet transmissions can recover the information x and y. Here again, we have just 6 transmissions, but all the nodes in the network have received at least 2 out of these 3 packets. More generally, if the source has k data packets, it encodes it into encoded packets, and this encoding is such that any node in the network, if it receives at least k out of these encoded packets, it is able to retrieve the data present in the original k data packets. Now, there are many codes in practice which have this particular property, such as maximum distance separable codes, fountain codes, etc. The algorithm that we have proposed is an amalgamation of 2 main schemes, coding-based schemes and probabilistic schemes. While there are broadcast algorithms which employ each of these schemes separately, this is a novel algorithm which combines both of these schemes that we have proposed. Let us see a simulation of the probabilistic forwarding with coding on the graph that we had before. Here I have 3 packets, x, y, and x plus y. The forwarding probability P is 0.72, which is lesser than what we had before, which was 0.8. Let me pause the simulations here for a moment. So the number of transmissions here is 146, which was similar to what we had for probabilistic forwarding, which was 147. However, the fraction of receivers is 0.752, which is much more than what we had in the previous case, which was 0.693. So let me resume the simulations now. But even with the lesser forwarding probability, we can actually get the fraction of receivers to be more while having the same number of transmissions. That is what this indicates. But why have we been able to reduce the forwarding probability? That is because we have an additional coded packet. So finally, we'll end up with the fraction of receivers to be 0.861 and the number of transmissions to be 161. But what are these fraction of receivers? These are nodes which receive at least 2 out of these 3 packets, since those are the nodes which can recover x and y. That is, these are nodes which are either yellow or blue in at least 2 out of these packet transmissions, and these are collected and shown as green here. In the following, the problem we target is that we fix this fraction of receivers to be a large fraction, that is 1 minus delta, say. And we are interested in the minimum probability for which this fraction of receivers is that 1 minus delta for some very small delta. We denote this by peak and delta and call that the minimum forwarding probability. Our performance metric is the total number of transmissions when the probabilistic forwarding is done with that probability pk and delta. Our interest is to characterize the performance of the probabilistic forwarding with coding algorithm on random geometric graphs. But what are these graphs? These are graphs in which nodes are distributed uniformly and independently at random in a square area, and any 2 nodes within a prescribed distance are connected to each other. Our interest on these graphs are because these are used to model deployments of ad hoc networks practically. On most well-connected graphs, such as these random geometric graphs, grids, or other lattice structures, such as the triangular and the hexagonal lattice, the performance of this probabilistic forwarding algorithm looks something like this. So here I have simulation results on a 31 by 31 grid with k equal to 100 packets. The first plot is of the minimum forwarding probability, and the second plot is of the expected total number of transmission. The x-axis in both of these plots is the number of coded packets n. Let us look at the red plot, which corresponds to a delta of 0.05. Recall that we want the expected fraction of receivers to be at least 1 minus delta, or 0.95. Firstly, the point here corresponding to k equal to n equal to 100 is the point which corresponds to the probabilistic forwarding algorithm with no coding, the second algorithm that I talked about. Notice that since there's a decrease because of additional coded packets, this indicates that introducing coded packets into the network actually helps in decreasing the number of transmissions, but at the same time ensures that 0.95 fraction of the nodes are receivers. Additionally, the point corresponding to the minimum, that is the number of coded packets, and the forwarding probability corresponding to the minimum are the optimal parameters to operate the network in order to gain maximum energy benefits. That is, at this point, there are least number of transmissions, but 0.95 fraction of the nodes are able to receive at least k out of the n coded packets. However, this kind of a behavior is not seen on trees. So here I have simulation results on a binary tree of I10 where the root is the source. Here again, the minimum forwarding probability decreases as the number of coded packets increases. However, the expected number of transmissions increases. It does not decrease. Why is this so? This is because on a binary tree, 50% of the nodes are there on the leaves. So if a leaf node has to receive at least k out of the n coded packets, Every node along the unique path joining it to the source needs to transmit the packet. In order for this to happen, the forwarding probability needs to be very close to 1, as can be seen from this plot as well. Now, so this means that even on addition of additional coded packets, each packet is being transmitted with probability 1, and hence the number of transmissions does not decrease. So notice that the main argument in the case of trees was because there was a unique path from the source to any node in the network. However, in the case of grids, there are multiple paths through which a particular node might receive the packet, and accounting for the probability of all these paths is hard. Hence, we resort to techniques from percolation theory and ergodic theory in order to come up with estimates for the minimum forwarding probability and the expected total number of transmissions. So finally, in conclusion, for the applications that we had before of the sensor network and the Internet of Things, if they form large, dense networks, then we can employ coding along with probabilistic forwarding for energy efficient broadcast. That's all for now. Thank you.